Good evening, everyone. Nice to be addressing you. I want to talk about colour. I've titled this, Everything You Know About Colour is Wrong. I found out a lot of things whilst I was researching this talk, and we're going to cover quite a lot of them. Let's get started, first of all, with about me. My name is Davidson. I'm the Principal Coding Manager at Creative Assembly. I've been working there on the Total War franchise for 20 years. 20 years. I'm a regular participant in WG21 meetings and telecons, and that makes me on the committee. Let's take a look at some of this. There we are, on the committee. I first achieved notoriety in the standards community by contributing to the graphics proposal P0267, but as a result of the poor reception that received, I decided to adopt a piecemeal approach and started work on a linear algebra proposal, which I've co-authored with Bob Stiegel. Along the way, I started work on a proposal to standardize an audio API for the library, and I'm also a co-founder of the #include diversity and inclusion group for C++ engineers. And I'd like to take a moment to talk about this. The biggest problem that we have in the C++ community is that there are more problems to solve than engineers to solve them, especially at this time. We need problem solvers to work on the hard problems. Historically, software engineering has been an inclusive environment. For example, Margaret Hamilton was director of the software engineering division of the MIT Instrumentation Laboratory, which developed onboard flight software for NASA's Apollo program. And she's one of the people credited with coining the term software engineering. But now, however, we appear to be heavily biased towards white men and have very low gender and ethnicity diversity. We as a species need to fix this. And if you're interested in helping, please visit the website and join the Discord server. There's over 5,000 of us there. Thanks very much. So this is our agenda. We'll look at identifying colours and how we apprehend intensity in colour. We'll look at a couple of colour spaces and a transfer function. And we'll see how colour management is widely misapplied. We'll take a quick look at the linear algebra proposal because it's actually quite relevant. And then finally, we'll see how colour can be used in C++ and review the proposed API. Now, presentations can be very dull, so I like to spice things up a little with artworks besides my own scribblings on my slides. And I will periodically ask you to identify works and submit your answers to the chat, just to check that you're all still awake. So any guesses who painted this? And there are extra points for the correct name for the piece. This is, of course, Jackson Pollock. This is number 34, which was painted in 1949. It's courtesy of the Pollock-Krasner Foundation. So you should now know where the chat window is. I hope you've been using it extensively all day, and how to ask questions, which Jens will field to me during the presentation. And I will attempt to answer questions as we go. So let's get started with another quiz. Please put your answers in the chat. Are you ready? What colour is this? What colour is this? Well, of course, it's white, isn't it? What about this? What colour is this? Well, that in fact is red. And this one? It's not hard, is it? So this is green. This colour. I really hope you're getting the hang of this now. It's blue. This one, still quite simple. Nice big blob of primary yellow. What about this? Well, this is the last of the simple ones. I would call this purple. This, on the other hand, what colour is this? Well, this is called teal, although I would have said turquoise or maybe aquamarine, but it's starting to get a bit more complicated. And how about this one? What colour is this? Well, this is orange, believe it or not, according to the PowerPoint colour picker. I'd have said, I don't know, brown or some kind of burnt sienna or burnt umber or something like that. I'd have taken a long, long time to actually arrive at orange. So let's talk about colorimetry. Okay. Now the problem we have is one of subjectivity and also context, which is the root of all ambiguity. So subjectivity, frankly, it's a pain in the behind. It is the home of opinions. It is the enemy of engineering, and it carries with it out-of-band information in the form of context. In the prior example, the out-of-band information was that the viewers were standing in different places and their answer depended on which position they were occupying. And this would change their viewpoint. This is very much like life itself and argument on the internet. So how do we eliminate subjectivity? The obvious, although not very useful answer is that we only consider objective criteria. We only look at those things that are agreed to be independent of viewpoint. So for example, if I spread my arms out and they disappear entirely from the camera, the distance between the tips of my middle fingers is 1.9 meters. And nobody can argue about that. We have a definition of a meter. And if we apply it 1.9 times to the distance between the tips of my middle fingers, we cover it perfectly. You can try arguing with me, but I would quickly discard you as a troll. The secret here is measuring according to an accepted standard, and everyone accepts the meter. Even the Americans accept the meter. But what about color? How do we measure human vision? Well, the first thing we need to observe is that perception is logarithmic. Differences at low levels are more significant than differences at high levels, and this is fundamental to behavior. It is evolutionarily advantageous. If you're being tracked by a predator, hearing a footstep in near silence is very valuable information. But if 30 beasts are chasing you, then hearing a 31st isn't valuable information. And the same is true of sight. If you perceive the amount of light that's cast by a single bulb, and then suddenly another bulb lights up, the effect is noticeable and it will consume your attention. On the other hand, if you perceive the amount of light cast by 8 bulbs, adding another one isn't going to make much difference to you. This is about the difference between contrast and brightness. Contrast is more useful than absolute brightness. Mechanical vision is linear. I've put vision in quotes because it's not really vision. It's photons hitting a CCD. This red, blue, and green diagram is a diagram of a CCD chip. Vision is about apprehension, understanding, parsing, contextualizing. And that's why it's logarithmic, because that's what is most useful. Machines just count photons using natural numbers. In fact, they don't even count the photons. They take a sample rather than counting the entire number. Now, the interesting information is at the dark end. Remember, contrast, not brightness is important. So we want to improve sampling at that end of the things that we store. The solution is to store the square root rather than the actual value, which gives us more values at the bottom in exchange for fewer at the top. Actually, I'm overgeneralizing here. It's not the square root. It's in fact x to the power of somewhere between 1 upon 1.8 and 1 upon 1.2. And this number is called the gamma value. But more on this in a moment. But you can see that low gamma samples more evenly across the spectrum than high gamma. So low gamma is good for bright pictures and high gamma is good for darker pictures. Now you store the gamma correction out of band in your data so that you can decode it properly. All right, quiz fans, who is this? This is Ophelia, painted by John Everett Millais, and there is a girls' school near to my studio named after him. Ophelia is dying in the water. Right, but what about colour? Now, there are two kinds of light-sensitive cells in the eye, rods and cones. Rods apprehend lower intensities, while cones apprehend brighter signals and also specialise over particular electromagnetic frequency ranges. There are in fact 3 types of cones specializing in different ranges. Now, they are labeled S, M, and L for short, medium, and long wavelength. And as you can see from the picture, the S cones respond to shorter wavelengths, peaking at 420 nanometers. And there are fewest of these. They make up about 2% of the cones in the human eye. The M cones make up about a third, peaking at 530 nanometers. And the L cones make up the majority and peak at the longer wavelength of 580 nanometers. Interestingly, in these days of nano processors, where we're carving processors with tracks that are just, less than tens of nanometers wide. This is less than the wavelength of light. I find that extraordinary. Anyway, you can see red, green, and blue as the primary colors here. 3 types of cone makes humans trichromats. Although originally we were tetrachromats, 4 types, until genetic mutation got in the way. I've heard it suggested that Van Gogh was probably a tetrachromat. And interestingly, women are much more likely to be tetrachromats than men, but they are non-functional tetrachromats. There has only been one documented example of a functional tetrachromat. She was found in 2016. But with 3 cones being the general case, we only need a vector of 3 values to represent all human vision. What we need is a way of transforming these electromagnetic emissions into perceived color. So to do this, you must take a standard human, put them in a standard environment, measure how they perceive electromagnetic waves by matching the colors of lights, and then build a function that maps electromagnetic wavelengths to human perception, giving 3 values, x, y, and z. And then we constrain this function so that all values are positive and luminance ranges from 0 to 100. Now, this was first attempted in a series of experiments in the late 1920s, and these results were combined by the Commission Internationale d'Éclairage, which in English is the International Commission on Illumination, into the CIE RGB color space, from which the CIE XYZ color space was derived. Now, not all values are possible. The ranges overlap. For example, S and L cannot both be 0. Now, engineering is messy. Engineering is real life. So the vector space defined by this color space contains impossible values. Now, we apprehend brightness separately from color. So let's create a color space to reflect that. We can normalize the values so that we have 2 values representing color and a 3rd value for relative luminance, informally known as brightness. And it's important to emphasize that Y is the relative luminance by deliberate choice. Now we have a 2-dimensional color space that we can vary by brightness. And it looks like this. This is the XYY color space, also known as the CIE 1931 color space. 1931. This has been going on a long time. Now, the figures in blue, in dark blue, are the wavelengths. X and Y vary between 0 and 1, and this diagram displays the maximally saturated bright colors that can be produced by a monitor. The area is called the gamut of human vision. Now, some interesting properties emerge. All visible chromaticities correspond to non-negative values of X, Y, and Z. And if you choose any 2 points of color on the chromaticity diagram, then all the colors that lie in a straight line between the 2 points can be formed by mixing these 2 colors. An equal mixture of 2 equally bright colors will not generally lie on the midpoint of that line segment. In more general terms, a distance on the chromaticity diagram does not correspond to the degree of difference between 2 colors. It's not a linear relationship. Also, if you choose 3 sources, you'll get a large range of colors, but you won't get the full range of colors visible to humans because this shape is not a triangle. There's so much detail about this. Do check Wikipedia for an introduction to CIE 1931 color space, but be advised that several people have written the Wikipedia articles, and there are slight inconsistencies here and there. Do take care. Now, I just want to call back to the earlier discussion on how we perceive brightness. Perceptual uniformity is a property where a small change in a value has the same effect in perceived color, regardless of what the value is. Now, values in this color space are not very perceptually uniform, which makes it inefficient. And there were 3 further attempts to achieve this, but they still exhibited some distortion. Now, in 1996, Microsoft and Hewlett-Packard created the sRGB standard. It's a standard. The International Electrotechnical Commission formally identified this in 1999. It's often the default color space for images that contain no color space information, especially if the image's pixels are stored in 8-bit integers per color channel. This color space is designed for monitors and printers in the World Wide Web. As you can imagine, it is the most widely used color space. sRGB defines the chromaticities of the red, green, and blue primaries, the colors where one of the 3 channels is non-zero and the other 2 are zero. These primaries are defined in terms of the CRYE color space, and they're based on the colors of the phosphors in cathode ray tube TV sets. You remember those if you have grey hair. And you might wonder if it's still relevant now that CRT devices are all but extinct. But you can make a tri-stimulus display that conforms to sRGB without using phosphors. You can use LEDs of the same color. And you can use any materials, actually, as long as the primaries match. So let's take a look at the gamut. Now, the triangle is the sRGB gamut shown within the CRYE 1931 gamut. It's all the colors you can see on an sRGB monitor. Each corner of the triangle is a primary defined in XY. It defines what R, G, and B relate to in sRGB in terms of the absolute XYZ definition. Now, you might be thinking to yourself, hang on, what about the colors outside the triangle? I can see those. Those colors, I'm afraid, are wrong. They are an interpolation. They're a representation. This image is drawn using sRGB. The only colors that are available are the ones in the triangle. The truth is we can't represent those colors on an RGB monitor or a projector. Don't get me started on Adobe RGB. The sRGB standard also defines a transfer function between the intensity of these primaries and the actual numbers stored. The function, as you can see, is nonlinear. And that word nonlinear is really important, and I'll come back to it in a moment. Now, on the x-axis, we have the stored values from 0 to 1. Now, if you store the value as 8-bit integers, it would be from 0 to 255. On the right-hand y-axis, also ranging from 0 to 1, you have the intensity. So the red plot is the sRGB intensities versus the sRGB numerical values. And behind the red curve is a dashed black curve showing an exact gamma equals 2.2 power law. As you can see, there is more detail at lower values. The upper half of the intensity spread is represented with only about 1/3 of the stored values. On the left-hand y-axis, you have the effective local gamma. So the blue plot is the function slope in log space, which is the effective gamma at each point. The gamma cannot be expressed as a single numerical value. This is important. The overall gamma is approximately 2.2, a number you may have heard, the line at the top. Particularly, 2.2 is the median value, the value at half intensity. However, the whole gamma range consists of a linear section near black, below a linear intensity of 0.00313, where gamma equals 1, and then a nonlinear section elsewhere, involving a 2.4 exponent and a gamma changing from 1 through about 2.3. And the purpose of that linear section is so the curve does not have an infinite slope at 0. This would cause dreadful problems. So, what does this function look like? Well, here we are. Now, it's actually in 4 lines. The first line creates RGB from XYZ. Now, this is a simple linear transformation by the power of matrices. But that isn't enough. We then have to do the gamma correction. And this comes in 2 parts, depending on the range. For small intensities, you simply multiply by 12.92. So those small intensities correspond to the linear part of the blue plot on the last slide. For larger intensities, you can see the rather unpleasant activity of taking the 5th power and then the 12th root. The 3rd and 4th line are the reverse operations going from RGB back to XYZ, and this is computationally expensive. I think you'll agree. Now, most of the time, all you want to do is convert your RGB values to a linear space so that you can interpolate. Now this means you don't need the matrix transformation, since that is simply another linear operation. So let's look at an implementation of the gamma correction from RGB to a linear space. So C underscore sRGB is the individual RGB value being converted between 0 and 1, whereas C-lin is the linear target value. That is a hefty piece of calculation. Performance is everything. And a very common approximation is to simply raise it to the power of 11 over 5. So on the right-hand axis, you can see the absolute difference shaded in green. It's okay, but it's fairly inaccurate. For example, if the values are quantized to 8 bits for the sRGB component value 197 over 255, the linear output is 145 instead of 142. Can we do better? Well, simply increasing the power a little to 2.233 recurring does improve overall accuracy, although it reduces accuracy slightly at lower values. But the real problem is that the power function is enormously expensive. At 3 evaluations per pixel for a 128 by 128 image, you're looking at nearly 50,000 calculations. You've got to do one for the R and the G and the B. Does it scale? Well, sometimes the power function isn't even available. You might be on hardware that doesn't offer something like that, and you have to manually approximate. And this approximation, a cubic polynomial, is actually rather cheaper, it's rather better, and it's available everywhere. As you can see, the differences are really quite tiny, less than 0.2 all the way along. But going back to sRGB is rather more problematic. So let's look at an implementation of the gamma correction from a linear space back to sRGB, where C underscore sRGB is the target RGB value, and C underscore lin is the linear source value. Now, the inverse of the original approximation, raising to the power of 2.2, is very, very poor. Please don't do that. But fortunately, a near perfect approximation is available where the linear part of the graph is clamped to non-negative numbers. Look at that, it's beautiful. But of course it does use power. So you can use a polynomial again. 3 square root calls should be faster than the power, but do check on your platform. So in summary, brightness perception is logarithmic. XYZ defines absolute perceptual colors. The XYY color space is linear. Linear interpolation is valid on linear color spaces. sRGB is defined relative to XYY, but the transfer function is not a linear function and it's expensive. sRGB is nonlinear, which means that linear interpolation is invalid on sRGB. I'm sorry this has taken me 22 minutes to explain, but there's a lot of background that you really do need to know to understand why color is wrong in so many ways. All right, time for another abstract. Who painted this? This is by Vasily Kandinsky. It's called Squares with Concentric Circles. It's from 1913. So, getting it wrong. We've taken a look at the theory of color measurement. We've learned about linear and nonlinear color spaces, and we've learned that sRGB is nonlinear. What could possibly go wrong? Right, here's a simple piece of interpolation. X plus y over 2. I'm trying to find the midpoint between x and y. What if the data being stored is in fact the square root? Square root of x plus square root of y divided by 2 is not the same as square root x plus y divided by 2. So consider x equals 9 and y equals 16. In the first case, we have 3 plus 4 over 2, which equals 3.5. In the second case, we have the square root of 25 over 2, which equals 3.535. The incorrect calculation is actually darker than the correct calculation. 3.5, it's less than 3.535. Believe it or not, midpoint is a remarkably subtle expression and easy to get wrong. Last year, Marshall Klaus spoke at several conferences all about it, and I really do encourage you to find his conference talks and look it up. It's an extraordinary piece of work. So new for C++20 is midpoint and lerp, the more general version for linear interpolation. So what does that look like in practice? Well, the top bar on this diagram, the top red to green bar, is a correct interpolation between red and green. The colour range has been correctly transferred to a linear colour space, but it's been interpolated and then returned to the original colour space. The bottom bar is an interpolation without transference. It is non-linear and it looks like a sludgy mess. It's too dark in the middle. I hope you have good bandwidth actually, otherwise this might look a bit blurry. Now this is an 8-bit sRGB perceptually linear ramp, incorrectly taking a round trip through 8-bit linear colour. You can see that the darker colours, those are on the top left, experience severe banding. We start off at 0 and then we suddenly jump to 13. And there is a quite significant precision issue. Now this effect is known as posterization. So this entails the conversion of a continuous gradation of tone to several regions of fewer tones, with abrupt changes from one tone to another. And you can see such an abrupt change at the start, 0 to 13. The leaps get smaller as intensities increase, and you will recall that sampling is at a much higher resolution at lower intensities. So you would expect the error to be much more profound at those levels. Now this was originally done with photographic processes to create posters with reduced colour depth, or when there were fewer inks available. And Wikipedia tells me it can now be done with digital image processing and may be deliberate or an unintended artifact of colour quantization. And it sounds like a rookie error, doesn't it? You wouldn't expect this in professional software. Sadly, I have to ask you to think again. My colleague, James Barrow, rolled his sleeves up and surveyed the landscape of code using colour. It was not a pretty sight, and I present now his findings. We'll start with STL. This is a popular cross-platform development library which provides low-level access to PC hardware. It has a number of pixel formats. This library features an sRGB mode which yields quantization, but there is no documentation about it at all. Now, SFML is Simple and Fast Multimedia Library, a popular cross-platform development library which provides low-level access to PC hardware. It also has a number of pixel formats, but this library features an sRGB mode which also yields quantization, and there are operator overloads on the colours, but again, there's no documentation about whether they're linear or non-linear colour spaces. Dear ImGui is a bloat-free graphical user interface for C++ with minimal dependencies. It doesn't support this at all. Alpha blending is wrong by default. It treats sRGB and linear colour as interchangeable internally, performing blending on 8-bit values which store sRGB. So that means it's hard to fix. It exposes 32-bit colour types in the API, which results in quantization if using an sRGB frame buffer, and again, no documentation. Flash was insanely popular until Adobe quietly put it out to pasture. The official documentation makes no mention of gamma correction. 8-bit sRGB colours are everywhere that are used like linear colours. It seems that there's no support for linear colour or gamma correction whatsoever, and again, no documentation. Unity. There is no documentation on the colour space here. Now, assuming this class is meant to store sRGB, then lerp is incorrect and the operators provided are incorrect. Assuming this class is meant to store linear colour, the colour constants are all incorrect. HSV to RGB is incorrect. Assuming this class is meant to store both linear and non-linear, then Unity has a global toggle for whether or not the rendering is linear colour or sRGB, which means that the interpretation of colour and the correct operations on it are a runtime choice. The documentation does not specify the colour space of the default colours. So overall, Unity's colour management is fairly brittle. Look at Godot. Again, no documentation whatsoever on the colour space, and many of the documentation samples skip over the concrete examples that would demonstrate one way or another, or they use weasel words to avoid specifying the intent of a function. So, assuming this class is meant to store sRGB, linear interpolation is incorrect, blending is incorrect, we check the source code, and grey is calculated needlessly and incorrectly. Assuming this class is meant to store linear colour, most of the constructors and the conversion functions are incorrect. Grey is calculated, again, needlessly incorrectly, and from and to HSV is incorrect. And this is a miscellaneous issue. In general, grey is calculated incorrectly as R plus B plus G divided by 3, regardless of the actual colour space. And lighten and darken are words used to imply something very different to what's actually being done. This class is overall very easy to misuse. OGRE. Again, no documentation whatsoever on the colour space in the official docs. Now, assuming that its colour class is meant to store sRGB, all the arithmetic operators are wrong. Assuming this class is meant to store linear colour, then the colour conversions are wrong. So overall, this colour class is extremely likely to be misused. So here's a picture of some cats. Any ideas who painted this? This is by an Austrian artist called Karl Kahler. He painted this in 1893 and entitled it My Wife's Lovers. Those are Turkish Angora cats. Anyway, as you can see, it's not great. This is some of the most widely used graphical software, and I don't like just iterating through software and saying, this is wrong, this is wrong. I don't like attacking my colleagues. I don't like highlighting their faults or anything like that. But I have to emphasize that color is wrong in so many places. And in fact, I'm only about halfway through the list. Let's crack on. Let's look at CRYENGINE. Now, there's a lot going on with CRYENGINE. James discovered 6 different representations of color in CRYENGINE. All of these. So we have the usual set of errors. So color TPL has arithmetic operators which can never be correct for a type of StudUint 8, 0 to 255. Other operators will quantize when t equals StudUint 8, and the color class can never store linear colors. And there's no documentation. So if these are sRGB color space, then arithmetic operators are incorrect. sRGB to RGB is lossy for color TPL. Scale col is probably incorrect. Lerp float will give unexpected results. Gray is probably incorrect. And if these are linear color space, then color TPL provides incorrect packing operators. To and from HSV is incorrect. And more generally, luminance calculation must be incorrect in one color space or the other. There doesn't seem to be a canonical color representation that functions take, which means that color management is ad hoc. So text to screen takes a float RGBA, set clear color takes a vec3, set fog color takes a color TPL, draw 2D label takes a pointer to float, and all of those functions are in the same class. Some documentation is just wrong rather than absent. This is a real problem. Qt, or Qt, I still don't know what the canonical pronunciation is, but it isn't too bad. Q color seems to be implied to be gamma encoded only, but a closer look brings up the Q color space class, which allows you to convert 32-bit QRGB values to linear color, their RGBA values. Now, this is not ideal, but you have to really want to shoot yourself in the foot here. So QRGB does have a Q pre-multiply function, which will produce quantization. But other than that, given that it's a UI toolkit, it seems to handle everything fairly correctly. There's almost no support for linear color in the API at all. But apparently, internally, it's all linear color and can be correctly rendered with gamma correction. So, win. Let's rush through the rest. MATLAB. RGB to gray uses an incorrect formula to calculate luminance, which assumes the NTSC color space. OpenCV's convert color with CV color RGB to gray uses an incorrect formula to calculate luminance, which again is only correct for NTSC. Now, SVG and CSS. Both of these perform blending in the incorrect color space by design. Now, this website also links to several articles reinforcing the content of this talk I'm giving you right now. Eric McClure writes, and this is a long quote, I'm going to read it out. The amazing thing here is that the W3C is entirely aware of how wrong CSS3 linear gradients are, but did it anyway, to be consistent with everything else that does them wrong. It's interesting that while SVG is wrong by default, it does provide a way to fix this via color interpolation. Of course, CSS doesn't have this property yet, so literally all gradients and transitions on the web are wrong because there is no other choice. Even if CSS provided a way to fix this, it would still have to default to being wrong. It seems we've reached a point where after years of doing sRGB interpolation incorrectly, we continue to do it wrong, not because we don't know better, but because everyone else is doing it wrong. So everyone is doing it wrong because everyone else is doing it wrong. A single bad choice done long ago has locked us into compatibility hell. We got it wrong the first time, so now we have to keep getting it wrong because everyone expects the wrong result. This is a counsel of despair. Alacrity is the fastest terminal emulator in existence, apparently. Using the GPU for rendering enables optimizations that simply aren't possible without it. But sadly, subpixel fonts aren't rendered correctly if sRGB frame buffers are disabled. MSys2 has a command line terminal called Minty. Color blending looks done incorrectly. There's too much color in the subpixels. The Windows console color blending also looks incorrect. Too much subpixel color. Microsoft Terminal seems to handle things correctly in clear type mode. Nice. But I will reserve my strongest praise for Unreal Engine. It is linear by default. It has a class called fColor and a class called fLinearColor. It has appropriate operators and it has full documentation. Right, finally, Linux has historically not had very good sRGB support due to the X Windows system. OpenGL is simply underspecified. So, for example, rendering to an sRGB-enabled back buffer, OpenGL and OpenGLES use different sRGB-enabled by default parameters, with OpenGL having sRGB disabled by default and GLES having sRGB enabled by default. And this results in bad things happening. For example, with Emscripten compiled OpenGL, they need a new name for that. The Linux NVIDIA bug, where the default frame buffer can't be sRGB, drives me again to despair. This is despair artwork. Can anybody tell me who painted this? This is The Desperate Man by Gustave Courbet, painted in about 1842. Fortunately, hope is at hand. Who can tell me who painted this? So this is Giving Thanks After Leaving the Ark by Enrico Morelli, about 1901. So we now know about colour. We've seen what can go wrong time and again. So how do we stop the world from making this mistake? How do we break out from this never-ending cycle of pain? Well, earlier I alluded to the Linear Algebra proposal. Now this is paper number P1385, and it's an important proposal because it introduces a consistent API and syntax for performing linear algebra. There's another linear algebra proposal in motion, which I'll talk about later, but this paper is informally called the syntax proposal. Now, there are a number of high-quality public and private linear algebra libraries in the C++ ecosystem, but unfortunately, they don't interoperate. And if you want to build something universal, then you're out of luck. You have to build something that operates with all of these libraries. So as a result, other languages like Python are stealing our lunch when it comes to things like AI. Now, by creating a unifying syntax, other library maintainers can use the customization points exposed in this paper to add their own optimizations. So the goals of the linear algebra proposal are to provide linear algebra vocabulary types, to parameterize orthogonal aspects of implementation, by which I mean I'm offering static polymorphism using template parameters. It offers defaults for the 90% of normal users and customizations for the 10% of power users. It provides element access, matrix arithmetic, and fundamental operations. And then it manages mixed precision and mixed representation expressions. And these last two items are important to a color API. So let's rattle through the nature of linear algebra. It's the branch of mathematics concerning linear equations and linear functions, and their representation through matrices and vector spaces. Now, a linear equation is the sum of known coefficients, that's a1 through an, multiplying a series of unknowns, x1 through xn. It's fundamental to analytical geometry and linear regression and solving simultaneous equations. Now, a vector is a tuple of scalars, and you can perform addition and the inverse operation subtraction if the operands have the same number of elements. You can multiply by a scalar, and you can perform an inner product, which is also known as a dot product. Vectors can be arranged as row vectors and column vectors, so a dot product is performed between a row vector and a column vector of the same number of elements. A matrix is a vector of tuples. Again, you can perform addition if they have the same size, along with the inverse operation, and you can also perform scalar multiplication like this. Matrix multiplication is a rather more tricky affair. It's not relevant to the colour proposal, but rest assured that the linear algebra proposal supports a broad range of applications. And those of you who are really familiar with the linear algebra domain will have heard of BLAS. This is also the subject of a proposal, so it has the name the BLAS proposal. The idea is to wrap up the C API defined by BLAS inside a C++ API. The BLAS API is battle-hardened through 40 years of use. When I first started writing games, BLAS was a year old. Now, this is an excellent proposal and is complementary to the syntax proposal, and the BLAS proposal and the syntax proposal are both targeting C++ 23, perhaps a little optimistically. Now, the problem of mixed representation is tricky, because C++ allows you to add a float to a double or a double to an integer. It performs the appropriate conversions silently and lets you get on with things without cluttering up the code. If it didn't do this, you would be stuck with casting instructions all over your code, but this isn't available for user-defined types. And of course it isn't. How would that work? And we already have this problem with the library-defined stud complex type. If you try and add a complex number of floats to a complex number of doubles, you get a compilation error. In the same way, you might expect the multiplication of a vector of floats by a matrix of doubles to also fail in compilation. Now, the library deals with this in quite a cunning way, but that doesn't matter to the colour proposal, but I will come back to this in a moment. The proposal also allows for substituting alternative algorithms for particular use cases. For example, if you have a sparse matrix, you may not want to use the regular multiplication strategy because it has a complexity of order n cubed. And you might want to use something a little more appropriate for environment. Perhaps you want to use Strasson's algorithm, which has a complexity of order 2.807. This ability to customize algorithm choices is very useful for a color proposal. Now, this is a really short summary, and I've already spoken at several conferences over the past couple of years about linear algebra and geometry. You can find these all over YouTube, and I'll be happy to answer questions about the linear algebra proposals later. But we do need to move on. So it's time for some more art. Who painted this? It's called Spring Sun. I'll give you a clue. Yes, this is Tableau 1, painted in 1921 by Pierre Mondrian. The first painting, Spring Sun, was late 1909, early 1910. So the obvious first question to ask is, why standardize color in C++? Well, it's been a long time since you could buy a green screen or a monochrome monitor. Colored text on a monitor has been available as standard since the last century. The last century, okay? You don't get to say that very often. All you need to do is power up a Linux shell and type ls to see colored text in action. It's a very useful cue for differentiating information. Here, blue is for directories, green is for files, but you can't write this in standard C++. You need to bind to a separate color implementation for your platform. Now, one criterion for considering something for inclusion in the standard library is if it's hard to get right. For example, it's very hard to write concurrent queues. Such an entity is being proposed for specialization. It can't come soon enough. As we saw from the earlier parade of misfortune, it seems to be very hard to get color right. And this is all well and good, but why teach it to C++? Well, there are three use cases that spring to mind immediately. The FMT library is a great leap forward in text output, but it doesn't handle color at all. A color proposal will allow output of colored text to the standard output. Now next, any serious graphics manipulation software is going to be written in C++, and this is where we have observed most of the problems with color, in C++ software. A color proposal will reduce the error here. And then finally, I have a proposal in flight to introduce a simple drawing library to the standard library. Having colour in the standard, as well as linear algebra, will reduce the bulk of this paper. And if we're going to have a colour proposal, what are the requirements? Well, it needs XYZ support and conversion between XYZ derived colour spaces. It needs compile time, user-defined colour spaces, and runtime, data-defined colour spaces. It needs to allow ICC profile implementation. We didn't cover that, did we? It needs to be strongly typed, and it needs high performance without storage or speed overhead. Now, American spelling. So basic colour space is our first struct, and it's a tag type like iterator category. Now from it, we derive two colour spaces, RGB and XYZ. So then we have a basic colour model, which tells us how to store colours. Now in the case of XYZ, this is trivial. It's a tuple of 3 floats. The RGB model is a little more interesting. It might be a tuple of floats or of ints, or even a mixture in some strange cases. Now alpha is always linear, so it's quite a simple type. We need alpha for composition. Now putting these together, we get a basic colour type. So this is simply a descriptor class that takes the colour space, the colour model, and the alpha model as template parameters and exports a number of symbols describing the space. Space type, model type, alpha model. And now we can create colour classes. So let's start with a standard RGB space over unsigned 8-bit values without alpha. So there we have it, sRGB uint8, basic colour over the standard RGB space over unsigned 8-bit values, no alpha. And then we get the same thing but with floats, sRGB float. sRGB is basic colour over sRGB space using the RGB float model and no alpha. So now let's add alpha. I hope you can see this is not quite rocket science. And then we get the same again, but with floats. So linear RGB looks like this. Basic colour over the linear RGB space using an RGB float model without alpha and with alpha. Float alpha in this case. And then finally, we need an XYZ class, the XYZ colour space. No alpha, of course. Now we need to be able to convert between things. So here's conversion between alpha models, pretty trivial. And here's conversion between RGB models. So we need to take 3 parameters, T, U, and V, and we need 1 and 2 for each of the models. And we have a contextual void because it's simple, it's just an arithmetic calculation that converts between RGB models. Now this beast, and it is quite a large beast I'm afraid, is for conversion between 2 arbitrary RGB spaces. So you can see that our parameters is a space, a model, and a gamma and an alpha twice, which completely defines your RGB spaces. Then we have conversion between generic RGB and XYZ. As you can see, it starts to get quite hairy. This is the other way around. So recall the transfer function was a simple matrix vector multiplication and a gamma correction function. With linear algebra in the library, we can customize implementations according to use case. So if you want something quicker than the absolutely correct function, you can substitute your own function. I'm going to skip over some of the implementation details and round off this section with the generic convert function that these enable. So there we have it. That's your simple conversion. Destination, source, and then all the arguments needed to describe the spaces. So that small set of objects is all you need to describe colour. And that about wraps it up. We looked at identifying colours and how we apprehend intensity and colour. We looked at a couple of colour spaces and a transfer function. We saw how colour mismanagement is widely misapplied. We took a quick look at the linear algebra proposal, and then we saw how colour can be used in C++ and a proposed API. So, was everything you knew about colour wrong? Thanks very much.